Good morning, everyone, and welcome to the Introduction to Flow Simulation. My name is Kurt Curtin. I'm a tech support engineer and trainer in the simulation products with MCAD Technologies. I'll be hosting you today and hopefully give you a good overview of the capabilities of the Flow Simulation product. If you have any questions along the way, don't hesitate to type them in the question box there in the webinar interface as the microphones are on mute, and I won't be able to hear you. So anyway, let's go ahead and get started. We'll be talking for about 30 minutes today. Don't want to take too much time out of your day. Here's our agenda, what we'll be covering. And so let's start with what is fluid flow analysis and why invest in it. Very briefly, fluid flow analysis is the simulation of fluid and heat transfer problems. It relates to any product that involves flow of gas or liquid with or without heat transfer and possibly forces on the solids. All of the usual reasons why it's good to invest in the fluid flow analysis, most importantly to reduce the cost associated with prototype testing. Overall, if we get the analysis involved in the process early, things are much more efficiently designed and developed. So why flow simulation? As with other simulation products within SolidWorks, we have direct integration with the SolidWorks interface and associativity with the 3D geometry that you develop in SolidWorks. As such, it's very easy to use. We have a very short learning curve with the program. Very good resources are also available regarding tutorials and training that we offer as a certified support VAR. And all in all, if we get the design validation early on in the process of the product development, we save both time and effort in doing so. You see there in red the conventional process where we try to analyze things at the last minute, resulting in design changes that are quite costly in terms of both the effort and the time required. So a look at some of the flow simulation capabilities. We can do internal and external flow, laminar, turbulent, or transitional. We can have rotating reference frames within the fluid. We can look at incompressible and compressible, Newtonian and non-Newtonian. And as I mentioned earlier, we can involve heat transfer, the full conjugate heat transfer with conduction, convection, radiation from both the ambient environment as well as solar radiation. So we do like to brag on the use of the product with various industries and various market leaders, and here's just a short list of some of the main ones that are making use of the flow simulation product. So some of the typical applications for flow sim, I'll give you a few of those. First of all, we can look at pressure drop across devices, things like pumps and fans. This allows us to get the most efficient design in our pump assemblies or fan assemblies. So pressure drop is one application for it. Also, we can examine heat transfer effects. So for things like heat exchangers, electronics cooling of internal electronic components on an enclosure, those types of things are quite conducive to the use of the heat transfer capabilities of flow simulation. We can do the heat transfer calculation with or without the flow. So we can include the convection effects of the flow, or we can just do the conductive effects, or even the radiation and conduction effects. It's also possible to look at the flow fields. We get a very good visualization of the flow field for flow problems, both internal and external. We can do things like predict cavitation, look at flows within intake and exhaust manifolds, those types of things. So quite powerful flow field visualization tools And we'll see an example of that when we get into the program here in just a little bit. Mixing processes, AC, duct design, spray nozzles, things where we have fluid mixing. We're allowed to introduce multiple fluids within the flow analysis and see how those mix together. As part of our little demo within the program, we'll be looking at an exhaust gas recirculation system in that very application. Force prediction. As we get the flow field set up, we'll get pressures that develop over things like aerodynamic surfaces on aircraft, wind loads on buildings, and the result of that pressure is that we can get force information out of that. As noted there with the asterisk, we are able to take those loads and use those within the finite element package, SolidWorks simulation. If we have that tool available to us, we can map that information over onto the studies that might be set up to handle that. I forgot to mention when we were talking about heat transfer effects, we can also bring that information over as well. So for instance, if we had a thermal stress problem that we wanted to solve, we'd be able to bring the temperature distribution from our flow project as well as convection coefficients over into SolidWorks simulation. So quite a good interaction. Another benefit to having the program working directly within SolidWorks, it interacts both with the 3D CAD geometry and the finite element analysis package. So let's jump into the SolidWorks interface and take a look at how flow simulation looks and feels. And the way we're going to do that, we're going to look at this two parts of exhaust gas recirculation system that might be in an automotive application. And we're going to look at a couple of different configurations of that to see which has the best mixing qualities. So I'm going to step over into SolidWorks. And so with this system here, what we're going to do, as I indicated, we have three configurations shown here within the top side of the tree. We get an add-in list here. If we look, we've got flow simulation added in. Once we do that, we get a new tab here within the SolidWorks interface. Notice we have the feature manager here on the left with all of the setup there for the assembly. And the flow simulation analysis tab looks this way. So for each of the three configurations in here, I've got one project, one flow simulation project set up. So we can have several what-if scenarios. So for this particular analysis, the olive-colored or the yellow-colored pipe would be the air intake for the engine system. So we'll have inlet air coming in here at about 50 grams per second. At, I believe, at 40 degrees C, and then our hot exhaust gases are coming in at 9 grams per second with 280 degrees C. So if I look at the definition of this one, we'll see that we've got that set up, thermodynamic parameters, 280 degrees C. Our substance concentrations, we've got air, both air and this exhaust gas, two different fluids within the system, the project here. And so for this one, you see we have the mass fraction of 1 for the exhaust side. And conversely, we'll have the mass fraction of 1 for the air side. And then for the outlet, we'll have just environmental pressure there on the outlet side. So with flow simulation, we can set up goals that allow us to get quality results for various parameters. So the parameters for this project, the parameters of interest would be the pressure drop in the pipes, the exit volume flow rate, velocity, and most importantly, the outlet mixing efficiency. So these goals allow us to get the quality results that we're looking for that's able to be post-processed in very nice ways once we've gotten results. So one of the things we can do when we jump down into the results here, I'm going to show the cut plot. So if I roll the model around here, you'll see this is a cut plot right now. Looking at the model, I can drag that through the model and see the various flow streamlines as well as, in this case, velocity parameters. Just let it update there again now to let it loose with the new position. Let's see here. Let me reload these results. Something happened there when I moved that. Okay. Well, I'm going to set up a new plot here. Something happened there with that one. Show you how that's done. So if I take turn off this section B here, so you see the full model. Go ahead and take a cut through here. Let's take a cut right through there in that plane. And we'll set up a new cut plot here. Let's look at velocity there. Okay. So there's our cut plot. We can move that to show the various positions, and you see we have velocities that are getting kind of stagnated there where this inlet comes in. Move this over here. We can also overlay the streamlines on that as I showed with that other one. Let me go ahead and do that for this one. Turn on the streamline plot. And there you see, as we get into these areas of the recirculation zones, we see that very nicely visualized there with the streamlines overlaid on our velocity plot. Surface plots allow us to look at parameters at the surface of the fluid as well as in the boundary layer. So I've got a surface plot shown here that shows all the interior surfaces, and we'll look at the mass fraction of that exhaust gas, and we'll be able to see how well the mixing is done with this particular configuration. So here we have, there again, the mass fraction of the exhaust gases. So you see the red is where the exhaust gas is coming in, and then the blue would be where no exhaust gas is. And then we get the mixing effect here. And as you can see, it's kind of concentrated in the lower part of this pipe. So not a very efficient mixing of the exhaust gas with this particular setup. And that's further confirmed by looking at the trajectory plots and the iso surfaces. So an iso surface plot is in here, and I've got there again mass fraction shown in an iso surface. So I can take a peek at that and update it real time as I change the value that I'm showing in the iso surfaces. So right now I'm looking at a value at a 0.25. So bring that up. Mass fraction of about 0.5. You see where that distribution is. And then all the way up to 1. So really powerful abilities here to visualize the flow. Looking at these flow trajectories, didn't want to edit them, I wanted to show them. Okay, so there again we see the fresh air coming in and being mixed by the red mass fraction of 1. And another nice capability of these flow trajectories is that I can animate them. You see you get extra visualization there. So as the goal is to get the best mixing based on these configurations, let's look at that. So I'm going to show you the others. So if I activate this one that's got an extended pipe in here, so this brings the exhaust gas further up into the fresh air flow, and then I've got one that's a turned exhaust pipe that brings it in and hopefully mixes it better. So 3 configurations to look at there. We have a nice, fairly new feature where we can compare the results from several models. So you'll see we have the ability. Before I do that, let me go ahead and turn on one of the plots here that will give us a good view here. Let me zoom into the exhaust, the end of the outlet end. Zoom into that, and we'll show one of the plots that are of interest here, this outlet profile, so that when I do my compare, now I can compare what's going on here at the outlet. So there again, back into the compare. You see we have the interface down here for that, and we're going to compare the active plot and a couple of other numerical values here from surface parameters and a goal, and we're going to look at that for all three configurations that we have projects for. Relating to configurations within the simulation, flow simulation, we can set up this for example, this default configuration, set it up as we like it. Then we can make copies of those, of each of those, or copies of that to reflect each of the others. So it's quite easy to duplicate the setup and then show results for each of those, calculate results, and get those in this compare mode here. So there we're done with the compare calculation, and we have this active plot you see here where we have the 3 different versions. I'm going to go ahead and activate that, turn it on within the Windows Photo Viewer, and we'll just look at those directly. So for the default, we see the higher concentration of the exhaust gas near this side of the exhaust pipe, or the outlet rather. Configuration number 2 that has the extended straight pipe extension. Now we see a lot better mixing here where we got a better distribution of the exhaust gas within that. And then the third one where we're looking at the turned pipe, we see we get once again a concentration of the exhaust gas, but just in a different area from the first one. So not much better there. So it looks like in terms of this outlet plot, we get the best distribution for the exhaust gases with a just short extended pipe going up into the fresh air pipe. So that's the compare mode. We have the other parameters that we can look at, the numerical values and the goal plot, or we can see the mass fraction in a numerical sense. So that's basically a look, an overview at the interface. Let's jump back into the presentation and look at a few other applications for flow simulation. Some more real-life examples. The first would be this electronics enclosure, a fairly simple representation where we have some heat sources in the microchips that are in here, and maybe a power supply, and a main CPU with a heat sink on it, and a fan bringing air into the back side of the enclosure and exiting through the vents on the front side. So the objective and the challenge is to identify and select the best heat sink shape that will be for this enclosure. A couple of different designs here that were analyzed. We have one with some smaller, shorter ribs along the entire width of the heat sink, and then one that's got some slightly higher ones there. So we want to look at those 2 different heat sinks and allow the engineer to simulate each and choose the best option. So after the projects have been run, looking at a couple of temperature cut plots with both of these showing the same 50 to 100 degrees F range, you see the difference there in the color color plot from heatsink 1 to heatsink 2. Looking at a top view for that same plot, and then so the results showed that about a 15% reduction in the solid temperatures occurred for heatsink number 2. So a very, very efficient way to come up with a good starting point for your design. Then that could be taken into to some prototype testing and further refined. Another example with a heatsink with some cooling fins is one involving natural convection. So we can turn on gravity and have the buoyancy effects working for us within the flow simulation. The previous one we showed some forced convection. If we had a situation here where we had a heat sink that we could not change, but we could modify, the surrounding areas, the challenge would be to how do we take this off-the-shelf heat sink and make it even better. So gravity direction shown there. A couple of or one modification that can be done would be to put sort of a shield on there to have sort of a chimney effect and funnel the flow, get a little higher velocity flow across the fins there. So let's look at some results on those two designs to see which one looks better. So here's a couple of plots that do that. Looking at velocities, so the lighter blue shows a higher velocity coming up through the heat sink that has the shield added to it. Greater velocity, greater convective effects. Here's sort of a cut view, a side cut view, where you see those velocities that have been augmented with the arrows that show direction and magnitude. So we get a pretty good velocity through here with the one with the heat shield, with the shield on it. And then a temperature plot where we can see a little bit more temperature distribution there on the one with the shield. And then looking at a temperature cut just through the solid, see the distribution where we have more dramatic cooling on the one with the shield. There again, the same scaling on each of the temperature plots. And so with the heatsink with the shield, we get a 10% decrease in the average temperature between the two. Let's look at one more real-world example. We have a challenge to identify the best screen shape for a medical suction device. So we have flow coming in through the bottom of this device, and there's a screen there, and we want to see which screen has the lowest pressure drop and results in the best flow through there without a lot of recirculation zones. So the designs here are shown for the screens. We've got one with triangular openings and one with circular openings. We just want to look at the flow rate for a given pressure drop for the two designs. There again, we can compute this information before the design is even prototyped to take the best direction for our prototyping efforts. So in terms of pressure profiles, they look fairly similar between the triangular and the circular cuts. Fairly similar pressure profiles and similar velocity profiles. There again, these plots have the arrows overlaid for direction and magnitude. But then if we look at some of the trajectories, there's a recirculation zone that's shown as the flow comes in. And the one for the triangular cuts has a little bit larger recirculation zone than the one with the circular cuts. So we see an advantage there with the circular cut model in terms of the recirc zones. And as far as the computed volumetric flow rate, we get a little bit better flow, overall flow through the circular cuts than we do with the triangular cuts. So I wanted to open it up to if you had any questions. If you have any questions for me related to the Flow product, I'd be happy to answer those questions at this point. If you have any questions, just type those into the interface there, and I'd be happy to answer those. While I'm waiting for that, what I wanted to do is to let you know that if you need more information about the product, if you're interested in getting maybe the more specific demo for your applications, you can contact us at the phone number listed here, 888-861-9659, or give us an email, info@mcad.com. Just let us know what we can do to help you evaluate the product better.